Hello everyone and welcome.
Hi, Ujay.
I will wait a couple of seconds. Maybe someone is joining, more people are joining. All right, so I hope everyone is fine and good. So today we will continue and carry on our recitation with the problem set number 3. Let me share my screen. I think someone was talking. Did anyone want to ask a question? Okay. Right, so let's begin with problem set number 3. Now, first of all, we'll start with question number 1. So in this question, we're supposed to compute MP for strong axis bending for each of the following cross sections. So part of this problem, we have section that is given to us wide flange in part A. So if we consider, first of all, this part of the problem in here, and since we are asked to find the plastic moment for this wide flange, given to us all the dimensions and the material for the steel, first of all, we have to draw lines where the section parts change in dimensions. So when I do that and draw the stress diagram, I would get something like this. So as you can see here, I have this blue lines where the rectangles actually change. So first of all, I have this point at top, then the shape changes here to the web, and I have another part here, and lastly at the bottom. So as you can see here, I have 4 blue lines. Now for the plastic moment, we have to consider that we have a plastic neutral axis. The plastic neutral axis is located at the middle or at the centroid of the member when it is symmetric. So as you can see here, this member is symmetric as it is wide flange and all the top side from here is symmetrical to the other side. Therefore, the plastic neutral axis is located at the middle. Now, another thing we have to consider that actually the section reached the plastic region in the stress diagram. Therefore, the stress diagram, as we can see here, is taking this shape as rectangles. Now, as you can see here, this can be considered as tension. This part is tension completely, and it changes at the plastic neutral axis, reaching 0 here, and this becomes compression. Now, moreover, since we understand this stress diagram in here, I have to locate the forces that I have. So from the stresses, we know that the force is divided by area, give us a stress. This is our stress Fy, which is given to us as 235 megapascal. So in order to calculate the plastic moment, I have first of all to find the forces in each regions in my wide flange. So for instance, I have the first region in here, this top flange. The top flange in here has a specific amount of force or stress. That's why I have, as you can see here, this force arrow. The arrow is representing the force, and I call it F, where it is force in flange top. And also, if I consider another part, which is this half of the web, I have force in the web, the top part, which is above the plastic neutral axis. Similarly, I have in here for the web bottom, and lastly I have for the flange bottom, below the plastic neutral axis. So as you can see here, I have these 4 forces, and now in order to calculate the plastic moment of inertia, I have to consider rotation about the point where the forces change from compression to tension. at the plastic neutral axis over here, where it reaches 0, as indicated in the blue arrow. So to move on with the problem, first of all, I have to calculate the force in each part. So I have to calculate the force in the flange top, the force in the web top, and these two. Now, since this shape is symmetrical, these forces in here would be equal to the forces over there. So if we want to calculate the force, for instance, for the force in the flange top, in here, I'm taking the stress Fy and multiply it by the area of the section that I'm concerned in. So this is the section I'm concerned in, the top flange. That's why I have B multiplied by the thickness of the flange, where B is 150 and the thickness of the flange is 12. Now I'm done with calculating this one. I'm going to calculate the force in the web, but in this part only, from here to there. So what's the area of this part? It is basically going to be D minus 2 times the thickness of the flange, where this is going to be D, minus 2 times the thickness of the flange divided by 2 would give us this length. And multiply it by the web thickness, which is going to be, in our case, 6 millimeters. And lastly, multiply it by the stress. Now, in this case, as I told you, since the shape is symmetrical from top and bottom, the force in the web top is going to be equal to the force in the web bottom. And also that goes for the forces in the flanges. Now, since I have the forces, I have to consider the moment rotation about that point that we were talking about, this one. So in order to do that, I'm going to multiply each force by the moment arm to the point that I'm concerned about. So for instance, force in the flange top multiplied by the moment arm from this force to the point. That's why I call it Y flange top. Similarly, I have to consider the rotation by the other force, if the force in the the web top multiplied by the moment arm in here, and I call it Y web top. So I have these two parts, and similarly goes for the bottom parts. Now, since this is symmetrical, so actually these ones are equal to those ones. That's why I can simplify my equation, and it would become, I can consider this part and multiply it by 2. Now, what is the moment arm for each force? So for instance, the force in the flange top, I multiply it by Y flange top, and Y flange top would be equal to D over 2 minus TF over 2. And that, in our case, would be equal to 181 millimeters. That's the moment arm for this force, FFT. What about the other one? I'm doing the same thing. I'm considering all the dimensions, and I get the moment arm equal to 87.5. Now plug in everything you have in the equation, this one, in order to get your plastic moment, and you would obtain the capacity of this section equal to 196.31 kilonewton meters. Now, you remember before, the plastic moment was equal to Fy by Zx. Now, as you can see here, we have Fy, but we don't have Zx from the table. We cannot find the plastic modulus from the sections table. That's why we had to do all this procedure. All right. Before I move on, do you have any questions, guys, about this part of the problem? All right. Seems like it is clear. I have a feeling, okay. So if we continue with the other part of the problem, part number B or part B, same question. Here we have a T section. Again, I'm considering I want to find the plastic moment about the strong axis. Therefore, I'm going to find like about this strong axis, the longitudinal one. So initially, as we did before, I have to draw my lines in order to draw the stress diagram. So first, I'm stretching this line, as you can see, this first blue one. Then I have another blue one where the section changes in dimensions. And then I have the last one at the bottom. So I have all my blue lines stretched. Now I have to consider where is the location of the plastic neutral axis. Why? Before, when the wide flange was considered, this section was symmetrical. But in our case, in the T section, this section is not symmetrical, and therefore the plastic neutral axis won't be located at the same location of the neutral axis. So the plastic neutral axis, this one, is actually going to be either in the web or in the flange. So how are we going to find that one? Where is the exact location? You have to start with an assumption. So in this case, I assume that the plastic neutral axis is going to be located in the flange. Let me erase some lines, so I don't want to make it like too crowded. All right, so, okay, I assume that the plastic neutral axis is located in the flange now. And I'm assuming that the distance yp from the top to the plastic neutral axis, I call it yp. Now, let me draw the stress diagram over these lines. So I have something like this, where this is compression. This side can be considered as compression or tension. And at the plastic neutral axis, it switches the force to tension, the opposite. And therefore, you get something like this. Now, put the forces on these, the stress diagram that you have. So I have now force in the top part of the flange and force in the bottom part of the flange. As you can see, it is below the plastic neutral axis. And also I have the force in the web. So I have now three forces. Now also you have to consider that the stress that is reached, here I have given that the material is equal, Fy is equal to 235 megapascal. So in the flange, the capacity is 235 megapascal, the yielding, and in the web, it is 355 megapascal. That's why you can see here that there is a variation in the stress diagram. 235 goes to 235, you're still in the flange, and then it goes to 355 because you're in the web. Now, since I have my forces, I will consider taking a rotation about this point in order to find MP, where the stress reaches zero. Now, before this process, as we said before, we have to find what is the value of YP. I have to find the location of my plastic neutral axis. So first of all, I have to find the forces. So we start with force in flange top. And if you want to find the area of this part, this area would be 235 Fy multiplied by this width, 150, and lastly multiplied by the whole height, you can call, which is Yp. So you're basically finding an area and multiplying it by the Fy. Now, if we consider the force in the flange bottom, similarly, it would be Fy multiplied by 150, still it is 150 here, multiplied by the distance, which is this one, sort of small. So in order to calculate this, the whole flange is 12. Now, since the distance from here until there is Yp, therefore 12 minus Yp will give you the remaining distance. So you get the force in the flange bottom in terms of Yp. And lastly, we find the force in the web. So what's that? Again, it's Fy, yielding capacity of the steel, multiplied by the area in here. So that area is actually 225 multiplied by 5. Now I have everything set in here, forces. I will calculate Yp from the equation of equilibrium, where the summation of all the forces is supposed to be equal to 0. So what am I going to do? I will consider the first part of the equation. This would be Ft. And these other ones taking the other direction. So this one would be FFB. And this one would be FW. Now I have all the forces set in the equation. I will go and calculate what is Yp. As you can see here, there is only one unknown in my equation, which is Yp. Okay, so if you calculate the Yp, it appears to be 11.66 millimeters. Now notice something very important. As you can see here, Yp appears to be 11.66, which is actually within the region of the flange. So the whole flange is 12 millimeters. If I got a value for Yp, which is 13 millimeter or anything that is above 12 millimeters, if Yp was bigger than 12 millimeters, you have to draw again your stress diagram and assume that the plastic neutral axis is located somewhere in the web. But since the value was in the flange, this is fine. Another thing, while you're locating the Yp, if the value appears to be nonsense, like you got a negative value, that means that there is something wrong. You have to try another location for the plastic neutral axis. So now in our case, it appears that the plastic neutral axis is located in the flange. Everything is fine. I can proceed and find the plastic moment. All right, so now going back to the same equation, I'm going to consider the rotation about this point over here. So similarly, like what we have done before, I will multiply each force by its moment arm. So this force multiplied by this moment arm, and this force by the moment arm to the plastic neutral axis, and lastly this force to the plastic neutral axis. So here we have the forces. We found that Yp is 11.66. You can substitute, you can get your forces in here, but you would have to find the moment arms, RFT, RFB, and RW. So if you calculate all of these, you would get something like this. And if you open the equation more, here we have all the forces calculated. This is the moment arm to the force in the flange top. And these are other forces and their moment arms. Calculate all this equation, you get your moment MP, which is equal to 47.46 kilonewton meters. So that's it for this problem. Do you have any questions, guys? No questions? All right, so I just want to make sure that you guys with me. So could someone speak up and tell me that you can hear me or everything is okay?
It's okay.
Yes,
Yeah.
everything is clear.
Okay, thank you so much. Now we continue to problem number 2. In this problem, honestly, this is a difficult one. This is not easy. If you can solve this problem, you can solve any other problems similar like to these ones, finding the yielding moment or the plastic moment. So this is like a difficult problem, and we will solve it together. So let's read the question. For strong axis bending, compute My, yielding moment, and the plastic moment, MP. As you can see here in this section, I have sort of like a pipe where it is a hollow from inside, and I'm given the steel yielding, the steel yielding capacity for this part, the rectangular part, and lastly this one, I have the yielding strength of it. So I'm given all the dimensions as well. Now, first of all, I'm going to calculate my. Let's focus at my first of all. Now, remember the equation my is equal to Fy multiplied by Sx, where Sx is actually equal to moment of inertia divided by y, or the distance from the centroid to the point of yielding. So as you can see here, I need these two things, the moment of inertia, and I need y, which is the distance from centroid to point of yielding. Therefore, I will start by finding the centroid of the whole shape. Y bar would be equal, I'm going to find the axis. The axis is supposed to be somewhere here, the x-axis. So Y bar, I'm considering that this is area 1, this part. The other part is area 2. And lastly, this part is area 3. I think so. I hope I did not confuse. Maybe it's opposite. Maybe this is A1, this is A2, and this is A3. Let's see. Now, in order to find Y bar, you know, from statics, this is very basic, but it's long to calculate. So Y bar in here, yeah, I confused actually. This is A1, this is A3. So 150 by 50, that's the area multiplied by the distance from my reference. I'm taking this reference, the bottom, 25. And you continue and you find the whole Y bar at the end for this whole section. And it appears that the location of the axis is going to be at 192.42 from the bottom. So distance from here to there to the centroid is going to be 192.42. Now, since I found Y bar, I can calculate the moment of inertia for the whole section. But before that, it's better to divide it into pieces. So you can divide these to pieces, and the summation of all the pieces, the moment of inertia for all the pieces would be I equal to I1 plus I2 plus I3. What are they? In here we have calculated the moment of inertia for the first part, number 1. Number 2, the other rectangular part, this one. And lastly, for the hollow section that we have in here, this is number 3. And notice I considered the parallel axis theorem, because the centroid of each part is far away with a specific distance. So for instance, if we consider this part has centroid over here, and the distance from here to the centroid, let's see what it is. 469. 469 is the whole thing. Minus 192.42. So if I subtract this distance, all right, so actually 469, let me check. 375 plus 88 plus 50. Actually, this here is not the whole thing. So just as an example, I will show you. Actually, the distance from here to the bottom is 469 if you check. Now, if you subtract the 192.42, you would get the distance between the centroid of this part to the axis, or the centroid of the whole thing. That's how we got the parallel axis theorem for that part, for instance. And it goes for all the other parts, 1 and 2. Sum all these moment of inertias after you calculate them, and you get the moment of inertia of the whole section equal to 570 millimeters to power of 4. Concerned about finding my, first of all, I have my object, and I will start looking at the stresses diagrams. So before getting into the stresses diagrams, first of all, you have to know that the neutral axis is located at the centroid of the whole object.
So we don't have any problem with finding the neutral axis. It is directly at the centroid of this section that we have. Now, the next point, we have to consider the stresses. So in order to calculate My, I have to know where is the first point that will yield. I have to know where is the first point that will yield from the stresses diagrams. So how would I do that? I have to make an assumption. Now, first of all, the yielding might happen either at point A, over here, at the top of this circular member, or at the bottom in here at point B, or we might have the yielding point at point C or at point D. So those are the critical points that we have. Now I have to make sure I will start with an assumption, and I will have to make sure that if I assume that such a point yields, it means that it is the only point that is yielding. So let's take a look now in order to get things more clear. Now, here I draw the stress diagram. Here you can see this is the zero line, and I am assuming at the beginning that the point A is actually going to yield. So I will draw a line. I will say that this is 355 megapascal. I will reach zero at the neutral axis, and then I will continue to the other direction. So from tensile, for example, to compressive, and I will end up somewhere here. Now I don't have any other value other than the 355 megapascal initially. So I have to start calculating now the stresses at points B, the stress at point C, and the stress at point D. Now, if you do that, using the triangle that you have already, we can use these similar triangles in order to find the stress. So how is that? First of all, you have the height of this triangle, 355, and you have the base of this triangle, which is 320.58. So 355 divided by 320.58 will give you the other small triangle that is included inside it. And as you can see here, I am interested in this height to find the stress for point B. So this is x divided by the distance from this point to here. So here I'm like sort of formulating the small triangle, and this small distance appears to be 232.58. So if you plug in all things you have, you find x would be 257.55 megapascal. That's the stress at point B. If we assume that the stress at A is 355, then the stress at point B is 257.55. Now notice something. If you compare the 257 stress with the stress values in here, that's 275 for this member, you will notice that the stress is less than the yielding stress. Therefore, we can continue. We are on the safe side. If it was more, I have to start over again my assumption and say that the yielding would first happen at point B, and I will give it the value of 275. But this is not the case. So I continue and check for the other points. I can check for point C, but I'm not doing that. I will check for point D. So if we check for point D, the same logic, the similar triangles. I'm using this big triangle, 355 divided by its base. And I can from here find this height. Now, of course, you have the base for this triangle, 192.42. That's the base, and we're interested in finding the height, and it appears that it is 213 megapascal. Again, if you compare it with the yielding stress for that member or that section, it appears that 213 is less than 355 megapascal. So as you can see, the only point that yields is point A. Therefore, my assumption is correct, and I can carry on with my solution. So now calculating My, so basically I have to substitute the yielding stress that we have. The yielding stress is 355. We have the moment of inertia for the whole object or the whole section. And lastly, we have Y. What is Y? It is the distance from the centroid to where you would have the yielding stress. and obviously it is 320.58. So if you plug in all the values, as I told you, you will realize that my is equal to 631.36 kilonewton meters.
I want to calculate MP. Now NP, since the shape we have is not symmetrical, there will be a shift in the plastic neutral axis. So the neutral axis was actually located in this part number 2, you can call it. Now I'm expecting that the plastic neutral axis would remain in this part number 2, but there will be a shift. So that's why I'm stretching a line from here, and I'm saying that the distance is going to be equal to YP. And again, I have lines where the section changes in order to draw the stress diagram. So when we draw the stress diagram, as you can see here, I'm assuming that all the parts has actually reached are above the yielding point. So in this case, since this is 355 capacity, this one's 275 and this one 355, this is how the stress diagram would look like. And of course it changes sides at the plastic neutral axis. So again, I'm going to find my forces, and I will actually calculate each force now. So if we consider F1, it would be 355 megapascal multiplied by this area, where this area would be equal to, as given to us in here. If I calculate F2, similarly, I'm going to calculate this area of this part multiplied by the stress 275. And you will have your F2 in terms of YP. You do that for the other forces, F3 and F4. And you can continue now and check where is the location of YP, exact location. So as we know, the forces in compression should be equal to the forces in tension to satisfy equilibrium. And I will actually take F1 plus F2 equal to F3 plus F4. So you will take all these things, sum them up, equal to all these things over here on the other hand side. And if you calculate YP from here, it appears to be 421 millimeters from top to here. This would be 421 millimeters. Now I have the location of the plastic neutral axis. I can go and find the moment about this point, where I basically need to find the moment arms now for each forces. So F1 to here, F2 to this point, F3 to that point, and it goes on. So if we do that, now I substitute the value of YP in my previous equations. And yeah, this is other YP. And since I have the forces, I found them now, I can find the moment about point P, or the plastic moment. So again, I'm multiplying by the moment arms. If you calculate the moment arms for each force, it would be like this. And again, just as a reminder, R1, for instance, would be the distance from F1 to the plastic neutral axis, and it goes on. So you will continue with this equation after finding all the necessary things. And this is how your equation would look like, with all the forces and the moment arms. Now, if you calculate this, MP, or the plastic moment of the section, would appear to be 917.6 kilonewton meters. And that's it for this problem. Do you have any questions, guys? All right. So I'm going. Yeah. Did anyone ask something? Seems like no. Okay, let's continue with the other problem. By the way, guys, I think this recitation will take like until 4:30. I'm not sure really how long it will take. So we will take a break after like 20 minutes. In case I forgot, please remind me. Okay, now we continue with question number 3. And here in this question, it says for all cases, consider the steel is 275. It means that if Y is equal to 275 megapascal. So for the following built-up I-shaped cross-section under strong axis bending, determine cross-section classification, compact, non-compact, or slender. So we have the case I or 2, 3, 4, 5, 1, 2, 3, 4, different dimensions. We have part A, part B, and part C. So let's begin with part A, and I will consider this case number 1 with these dimensions. So I have all the dimensions that I used from the case number 1 set on my section, and I have to decide whether the section is compact or non-compact or slender. So how would I do that? First of all, I have to consider flange, and then I have to consider the width. So if we consider the flange part, check for the slenderness of that or the compactness of this part. First of all, I have to make use of AISC table 4.1b. So if we go to the table for this step, notice that it says for the following built-up I-shape cross-section under strong axis bending. Bending is very important. Why is that? Because when you go to the tables, you will see that you have this table 4.1 A and B. Now in here it says members subjected to axial compression, but in my case the section is actually subjected to flexural bending. That's why I'm going to look at this part of the table. Now in our case it was a wide flange. So in order to check the compactness of the flange only, I have to read the description of the element. So in the description, for instance, here it says flanges of rolled I-shaped sections, channels, and tees. So this is my case. I have a wide flange, and I'm considering the flanges only. Therefore, to check the compactness, I have to calculate B over T. So what is B over T? B is this distance given to us in here in the drawing, and the thickness T is the thickness of the flange. So if you calculate this, BF I said divided by 2, because I'm concerned about this part, half of it, and multiplied by the thickness of the flange. Therefore, it would be 300 over 2 by 20, and you would get 7.5. Now I have to check the value of lambda of my section. Is it in between the lambda p and lambda r, or less than lambda p? Now, if it was less than lambda p, it means that your section is compact. If it appears that your lambda is between lambda p and lambda r, it means that your section is non-compact. Okay, what if your lambda is actually bigger than lambda r? The section would be slender, or the flange would be slender. So first of all, I'm going to check lambda p. And here it says that the equation is equal to 0.38 square root of E divided by the yield strength of the steel. So I substitute everything in here, and it appears that this value would be equal to 10.04. If you compare your lambda with lambda p, it appears that it is less, therefore the flange is compact. And we're talking about case 10. This is case 10 here, I said, and this is the case in the table. Okay, now I check the flange, it appears that it is compact. I have to check for the width. So for the width, I have to consider another case I have to read. So it's not here. The one that is above, it's talking about flanges. This one is talking about widths. Webs of doubly symmetric eye-shaped sections. Case number 15 is talking about what we need. So in here, in order to calculate my lambda of this web, it's going to be h divided by tw, where h is given to us in the drawing, and tw is the thickness of the web. So let's calculate this. 1000 is my h, and the thickness of the web is 10. Divide them, you would get your lambda of the web equal to 100. Now check lambda p in order to see if it's less or more. So 3.76 multiplied by this value inside the square root, you would get lambda p is 101.39. Therefore, your lambda of the web is actually less than lambda p, and the web is compact. Now notice something, since the flange and the web, both of them are compact, I can say that the whole section is compact. And therefore, that's the conclusion of the whole section. You say it is that the whole section is compact. And you can do the same things for other cases, like case number 2, 3, and 4, and you will see like the differences. But I'm skipping this in the recitation since it is repetitive. Now, if we consider the other part of the problem, the part B, it says repeat the same problem for weak axis bending. So first of all, we were considering strong axis bending. Now we'll consider the weak axis. So let's check the compactness of this member in the weak axis. So again, I have to consider the flange. If I check my table for the flanges, here I have something. I'm not going to use this part. Why? Because it's about the strong axis bending. If you take a look at here, it says flanges of all eye-shaped sections and channels in flexure about the minor axis. So it's about the weak axis. Therefore, I'm going to make use of case number 13. And in order to calculate lambda, it's going to be b over t. So if we substitute everything in here again, you would get similar value to what we obtained before, 7.5. And if you check for lambda p, as in this equation, it appears to be 10.04. Now, your lambda is less than lambda p, therefore the flange is compact. What about the web? Well, since you are actually going to bend about the minor axis, we are not considering the web. And if you check in your table, you don't find anything talking about the web when the member is actually in flexure about the weak axis. So if we check in here, we find nothing. Therefore, you don't consider the web. So basically, by checking the flange, it is compact, therefore the whole section is compact. When the case is about rotation for weak axis bending. Okay, now, do we have any questions?
Yes, Madam, can you explain why we don't check for web?
Can you say it again, please?
Can you explain why we don't check for web minor axis? Briefly.
Why double check about what? I couldn't really understand.
Why we don't check for web in bending about weak axis?
Well, if you consider the web, for instance, let's take a look at this drawing, for example. Where's my pointer? So I want to bend about my weak axis. Now, this is the axis where I'm bending. And in here, as you can see, the effect, or when you calculate the moment of inertia for the web about the minor axis, is very negligible. Therefore, we decide about the compactness of the section based on the flanges, because in here, if you consider the parallel axis theorem, there is a big distance between the centroid of the flanges parts to the whole center, to the axis of rotation. So therefore, because the whole axis of bending is passing through the web, and the web is already very thin, it's negligible, and it is not considered. And the decision is made based on the flange compactness only. So the web is ignored. You don't take it in the case of weak axis bending, but it is important to consider it in the case of strong axis bending. And here it's going to make a difference with me because it's making moment of inertia more. So it's taking high role in the calculations.
Okay, thank you.
You're welcome. Any more questions? Okay, so let me continue. All right, so in here, in this question again, question 3, part C, it says classify the following built-up box shape cross sections under strong axis bending. Okay, so let's see. Now this time, instead of having a wide flange, I have this box shape, and it says classify it under the strong axis bending. Now again, I'm going to consider one of the cases, case number 1.
So now if we check for the flanges, first of all, we have to find the compactness of the flanges. And for that, I have to move to the table that is in AISC. So if we go to the table, and we will be taking a look at the members subject to flexure, of course. In this case, when you take a look at the examples that are provided, you have case number 17 and case number 19. They are talking about the box shapes. But since we are concerned about the flanges, case 17 is what we need. And for that, we consider the flanges. We take lambda as B over T. The B is shown in the example in here, and T is the thickness of the flange in the box shape we have. And we can decide the compactness by comparing with lambda P and lambda R. So if we check for the lambda we have, B over T, if we want to calculate that one, as we said before, T is this one, this is T, and B, from the example we saw before, this would be B. Now, in order to calculate B from what we have, B is basically equal to BF minus 2 multiplied by TW. And that's what you see over here. 300 minus 2 multiplied by 10. 10 is the thickness of the web. So that's B. Now what about the T value? T is basically TF, and you take it as 20. So if you calculate that, you get your lambda equal to 14. Now, if we check for lambda P again, in case 17 that is provided in the table, is 1.12 multiplied by square root of modulus of elasticity divided by the yielding stress. And from here, if we substitute the values that we have, we get lambda P equal to 30.20. Now, we don't have to continue and check lambda R because obviously our lambda is less than lambda P. Our lambda is less than lambda P, and therefore the flanges are compact. Now going to the second part of this problem, checking the web of the section that we have to go back again to the section or the table that we have in the AIC. And if we look at the cases that we have, the one that would suit us is case number 19. And if you take a look, it says webs of rectangular HSS and box sections. Now from here, in order to calculate the lambda, it would be basically H divided by T. So what is H? From here, you can see from the drawing, H is the distance from here to there, and this is the T value, the thickness of the web. So if we want to apply that, this is our T value, and this is our H value. So here's how we calculated the lambda for the web. It is 1000, that's H, and divided by 10, the thickness of the web. That would give you 100. Now, after that, I have to calculate lambda p. Lambda p is again can be calculated from the table in here, 2.42. And if you substitute all the information that you have, you get your lambda p equal to 65.25. Now, obviously, our lambda now, this lambda is bigger than lambda p. But I don't know, is it bigger than lambda r or not? So I have to calculate lambda r now. Now, if we check for lambda r again from the table, lambda r is shown as 5.7 this time. So substitute all the values, and get your lambda r is equal to 153.75. Now, as you can see, your lambda is actually falling in between lambda p and lambda r. And therefore, your section is actually non-compact. Now, since we have the flanges are compact and the web is non-compact, the overall section would be non-compact because the webs are more critical than the flanges. And therefore, we decide and say that the whole section is non-compact.
So let me solve, let's see. All right, I will solve this part, the last part D, then we can take a break, guys. So in this part D now, it says classify the following sections under axial compression. So it's important. Before we were talking about the bending, now we are talking about axial compression. And you have to specify whether it's non-slender or slender. Before we were saying compact, non-compact, and slender. But in the axial case, it's different. So if we consider, for example, this shape, this pipe, and go back again to our table in AIC. Now this time, the flexure is not going to work since I'm concerned about the axial. So I have to check the table above. And the table that I have in here says axial compression, members subjected to axial compression. Okay, so I had that pipe. I'm checking the examples. Here's my case number 9, in order to check the slenderness. So it says divide D by the thickness. And if you do so, the outer diameter is 800, so this is your D from here until there. Divided by the thickness, this is your thickness, 8, thickness of wall, you can say, and you get your lambda 100. Now let's check another part. What is this? The column in here is lambda r. So if your value was less than what we have in here, your section is non-slender. If it was bigger than this value that appears in here in general, it would be a slender case. Now going back to our example, 0.11 multiplied by E divided by 275. So let me see. All right, so there isn't a square root actually in here. So there is this to be cancelled. This is a typo. Again, let me take a look. Okay, without actually the square root, this is 80. So the values are correct, but you just have to neglect the existence of the square root in my slides. So as you can see now, lambda appears to be bigger than lambda r. And if we check again here, when your lambda is bigger than lambda r, the section is going to be slender. Therefore, I said the section is slender. Okay, now if we check another shape, I have another wide flange, but it's under axial load. So I'm going back again, I'm going to check this table. And in here, I have a wide flange. So as you can see here, flanges of rolled I-shaped sections. It says in case number 1, the lambda is B over T. And if we calculate B divided by T, as we see from the drawing in here, this is your B and this is your T. Sorry, this is your B in here and that's your T. Okay, so we check lambda, it appears to be 12.5. What about lambda p? Lambda p as given to us in here, 0.56. So multiply that, you get lambda p equal to, or lambda r to be exact, lambda r appears to be 15.1. Therefore, since the lambda is less than lambda r, the whole flange is non-slender. Okay, what else? I have to check for the web. Okay, there is another typo in here. This is supposed to be web. So I check for the web now. I'm going back again to my table. In here, for the webs, it says h divided by tw. So if you check the drawing again and do as shown, 700, this is your h, divided by the thickness of the web, 12, it gives you lambda equal to 58.33. Now if we check for the other lambda that we need, we see that for the web case, case number 5, it is 1.49. So 1.49 multiplied by the whole value we have here is 40.18. So as you can see, for the web, your lambda is actually bigger than lambda r. Therefore, the section is slender. So in here, you see that the web is slender, but the flanges are non-slender. So what are you going to say? You would say the whole section, flanges and web, would be actually slender, because the slenderness is critical in the web. Therefore, the section is slender. Okay, do you have any questions, guys, in here? Okay, since you don't have questions, let's take 10 minutes break and come back. We will continue with other problems, problems number 4, 5, and 6. All right, guys? Guys, you there? Are you sleeping?
Yes, I'm okay.
All right, thank you. Let's take the 10 minutes break. So we're back again. I will start sharing my screen again and continue solving the problems. Okay, now we will continue with the problem number 4. So in problem number 4, if we read the question, we're supposed to find the lightest I shape of S355 steel with a given steel yielding capacity. And we're supposed to consider all these shapes that are given to us. IPN, IPE, HEA, HEB, and HEN. There are too many sections to try. And we are given the distributed load, distributed dead load, and the distributed live load as it appears in here, 60 kilonewton per meter for the live one and 30 for the dead one. And it says consider LRFD and ASD separately. So in solving, I have just considered LRFD. Also, it says beam is provided with adequate lateral supports so that lateral torsion and buckling does not control. And we have a serviceability requirement in here. So as you can see, if you take a look at this beam, we have a roller support in here and we have a fixed support. And we have the distributed load. So we are going to design and find the lightest section, wide flange section. So if we start in considering this problem, first of all, to find the section, I need to start with the plastic modulus of elasticity. Before that, I need the maximum moment that will be applied. And before that, I need a distributed load. So let's consider the distributed load that is going to be applied in here. So in the live load and the dead load, all of them are given to us according to LRFD. If you multiply 1.4 by the dead load plus 1.6 by the live load, you would get the value of the distributed load equal to 132 kilonewton per meter. That's the factored load. So I have the factor distributed load. Now I'm going to find the ultimate moment that is applied on my beam. So how would you find the ultimate moment as a reaction from the distributed load? Well, you have to actually draw the moment diagram. And if you want to consider such a system like this, roller and fixed support there, it's actually indeterminate to the first degree. So I'm not going to get in that detail. I'm just going to basically show you how the moment diagram would look like. So for instance, for this case, again, we have the distributed load. Here it's called Q. Here we have the roller support. If we consider the moment diagram, the maximum moment that would be applied by the distributed load would be equal to MA at the support, where MA would be equal to QL squared divided by 8. So in my case, Q is actually W. WL squared divided by 8, where L is the whole length of the span, 12 meters. So as we found, the distributed load W is equal to 132. I multiply it by the span length squared divided by 8. And that is the maximum moment on the beam. Therefore, you would have ultimate moment from the load equal to this value. Now, we have to proceed and continue with an assumption that this section is compact initially. So I will assume that the section that I will pick is compact. And by that assumption, I'm allowed to use this equation. I'm going to say that the capacity of my member, Mn, is equal to the applied load or the applied moment on the ultimate moment on the beam. And by that, I'm going to say Fy multiplied by the plastic modulus multiplied by 0.9 by LRFD, the load factor. Now, I have Mn, I have Fy, and I have 0.9. I have to find Zx, the plastic modulus. So Zx would be equal to 7,436 centimeter cube. And since I have a value in here, I can start searching in the sections, in the section tables, where the value should be above this Zx. So you can say that this is Zx minimum. And it said to us previously that you have to check IPN and all these other sections. So to save time, I just picked one of the sections, and I'm going to continue with HEA 800. So in this section, the plastic modulus is equal to 8,699 centimeter cube. Now we have to check for the compactness of the section before we continue solving. So if we check for the compactness of the flange, again, just similar to what we have done before, we go back again to the tables of AISC in here and notice that this is under flexure. You will check which case is suitable for you. It is a wide flange, and you would carry on. So no need to repeat that. We check for the flange. It seems that it is compact. We check for the web, and again the web seems that it is compact. So the flange and the web, both of them are compact. Therefore, the whole section is compact section. And remember, in the question, it said to us that the beam is provided with adequate lateral support so that the lateral torsion buckling LTB does not control. So now I can proceed. My section is compact and everything is fine. I can now use this equation where MP is equal to 0.9 Fy by Zx in order to calculate the capacity of HEA 800. I want to check the capacity whether it's bigger than M ultimate, which I found in here. So let's see. Now, if you plug in all the values of the section properties, this is Zx, this is Fy, 0.9. Here it appears that the capacity of this member, the MP, plastic moment, is equal to 2,779 kilonewton meter. And it is bigger than this value, which is mu, the applied or the ultimate load by the distributed load, which we calculated in here. So this section is good. Now I have to proceed and check for the shear. I want to check for the shear capacity, if it's adequate or not. So again, similar to what I have done in here, I consider the ultimate moment by the distributed load, mu. Now I have to consider the ultimate shear force that is applied on my beam. In order to do that, again, you consider the ultimate shear that you would have. And if you check the shear diagram, V1 in here, and this shear diagram would be the maximum value, where the maximum value is going to be equal to 5/8 WL, where W is your distributed load, factored load, multiplied by the span length. So from here, the ultimate load that is applied on your member is 990 kilonewtons. Now I want to check the capacity of my member, the nominal shear capacity of my member. So I'm saying Vn equal to 0.6. And I'm considering the area of the web for the section that I have. I'm neglecting the flanges area because 96% or above of the stress, the shear stress, is distributed or taken by the web. Therefore, the flanges are ignored. So area web multiplied by Fy, and you substitute everything you have. So these values, I took them from the section tables, 790 by 15. That's the area of the web. And you get your nominal capacity equal to 2,524 kilonewtons. As you can see now, if you multiply it by 0.9 LRFD, according to LRFD, it appears that it is again 2,200, which is bigger than 900 kilonewtons. That is good. It is the capacity is more than the applied load on my member. So this is satisfied. So I check for the moment, satisfied. I check for the shear, it is satisfied as well. Now, before I continue to the deflection, let me tell you something. So in here, it seems like HEA is adequate. HEA is good to be used. In such a problem like this, in a design problem where it asks you for finding the lightest eye shape, you don't basically try one section and once it goes fine, you say this is the one. You're supposed to try multiple sections. So you're supposed to pick some sections from IPN, IPE, etc. And if you had a collection of sections, like let's say IPN, I don't know, say 100, IPE 200, I don't know, maybe like this, HEA 800, as we found. Let's say that all of them actually satisfy the capacities, like in moment and shear, this one satisfy and that one satisfy. All of them satisfy. What you have to do is basically pick the lightest section. And as I told you before, in order to pick the lightest section, you go to section tables and you check for the first column in here. So the first column in here, it says, for example, IPN 100, 8.3 kilogram per meter. You will compare and pick the lightest section based on the first column. Okay, so this is the case I wanted to make clear. Now going back to the last part of the problem. Now we check for the deflection. Let's say to us, service live load deflection should be less than or equal to L over 360. So I'm going to check if the condition is satisfied or not. All right, let's see. So what is the deflection for such a case where you have a beam where it has a fixed end and a roller support in here? Now again, I'm making use of this website. to make things short. All right, so let's see. Delta max, it says my delta max is in here. WL to the power of 4 divided by 185 EI. That's for the case where you have distributed load, fixed support, and roller support. So by making use of this equation, here what I have, now instead of writing 185, I wrote it 2 divided by 384. Should be the same. And I have this part. Now focus on something. EI, I know them. The length, I'm going to consider the whole span length, which is given to me in the question as 12 meters. What about the W, the distributed load? Well, since it said to you in the question that you're going to consider the serviceability of the live load, first you have to consider that distributed load would be 60 kilonewton per meter unfactored, plus the dead load or the weight of the member, because the weight of the member is always there. So you have to consider it along with the live load. And here you see 224, it was kilogram. I multiply it by 9.81 gravity acceleration in order to convert it to kilonewton per meter. And I obtained that value from the section tables. So sum these two values, you would get 62.2 per kilonewton per meter and multiplied by the span length. Substitute everything else and you would get your deflection equal to 11.06 millimeters. Okay, 11.06 millimeters, if we applied such a load like this, live load only, and notice it says you should compare it with this value, L over 360. So is this condition satisfied? We had here 11.06. Is it less than or equal than 12 divided by 360? So if we check that and compare, it appears that it is actually less. This value would be 33 millimeters. Therefore, 11 is less, of course. So the beam is satisfying all the conditions. It is satisfying the moment capacity, the shear capacity, and the deflection. Do you have any questions about this, guys? Okay, I'm moving on to question number 5. Now, in here it says, for the beam shown below, determine the maximum value of distributed load. Just determine the maximum value of distributed load, W, calculated according to ASD, load combinations. Lateral supports are at the ends only, and you're given the steel characteristics, and you're not supposed to check for the deflection in here. So as you can see, we are given the section properties, all the dimensions as well, but we have to find what is the maximum distributed load that I can apply. So how would I solve this problem? First of all, I'm going to check for the compactness of this section. Now, if you check the compactness, and again, if you check case number 17 and case number 19 from the AISC, you would get the flange compact and the web as well. Therefore, the whole section is compact. Now, if I continue, in order to calculate MP, the plastic moment capacity, I have to consider, as in the first questions, if you remember, we were calculating MP manually. I have to consider again the forces from the stress diagram, F1, F2, F3, and F4. And since I'm given in the question all the required dimensions, so basically you will multiply the stress by the areas. So this area, for example, goes to F1. Then you have F2, you have this area and that area. Similarly, F3 would be equal to F2, and F4 would be equal to F1. If you set the whole equation properly, you would find that MP, the plastic moment capacity of this member, equal to 1082.95 kilonewton meters. Now, from the plastic moment, the capacity of the member, I can find the ultimate moment that the member can take. The ultimate moment, now when you think about a case like this, a simply supported beam, you have a distributed load, and you draw the moment diagram, the moment diagram would look like something like this, where the M max is going to be equal to WL square over 8 kilonewton meters. So that's how I have this. I'm saying that M ultimate is equal to distributed load, where it is unknown in my case still. And in order to solve the problem, I'm going to assume that mu is equal to mp. Therefore, I take my W outside, I'm calling it W from moment, and in here I manipulate everything. So the equation appears to be like this, where mu is equal to 1082.95 kilonewton meters. Calculate this, and you would obtain the maximum distributed load you can apply, 64.05 kilonewton meters. Are we done? Not yet. You have to check for the shear capacity as well. So if we check for the shear capacity, again, 0.6 multiplied by Fy multiplied by the area of the web, 460 by the 460 is the distance from here to there, multiplied by the thickness, 10, multiplied by 2 because I have two pieces. So that's the area of the web of this section. And lastly, you would get the nominal shear capacity of this section equal to 1,518 kilonewtons. Now, I have to compare it. What am I going to compare it with? Well, again, you know that the shear, if you draw the shear diagram for such a case like this, it would be similar to what we have in here, where the maximum value would be WL over 2. Now from here, similar to what we done before in there, if you manipulate your equation, you would get the value of the shear that is applied, or the distributed load by shear capacity, 201 kilonewton per meter. So in here, as given to me from the equations, that based on the moment, it can take up to 64 kilonewton per meter. But based on the shear, it can take up to 201 kilonewton per meter distributed load. Now, which one am I going to consider as a distributed load? I will consider the smallest one, because obviously if I exceed the 64 kilonewton per meter, it will fail. The member would fail. It won't even reach to 201. Therefore, the moment capacity is limiting, and distributed load is equal to 64.05 kilonewton per meter. Now, do you have any questions, guys, about this problem?
Yes, Hocam, I have a question.
Yes.
Hocam, if our section was non-compact, we would still solve the question according to MP, right?
Well, no, it would be different. You have to consider the equations based on this diagram or plot, where you have here MP, here you have another value, you have another equation to find the moment capacity, and here you would have another value for the moment. So in here I have lambda p, and in there this would be lambda r. So since it was compact, it was easy to calculate. But if it was in between here or there, it would be different. You have to use different equations. And the equations that I'm talking about, you can find them in the AISC. Let me see. So from the AISC or your even notes, class notes, all right, design of Flexural, members of Flexural. Okay, we are almost there. All right, so you can see, for instance, we have the equation F22. Now it is given to you that Mn is equal to this equation, and that applies to which part of the graph? This would apply to this part, equation F22. And this part would have another equation where it is this value. So FCR is given to you as in this equation. So it would be different. The calculations would be different based on these equations. All right.
Okay, Jim.
Any more questions, guys? Okay, I'm moving to question number 6. Now, in this problem, I have a beam. It says beam IPN 500. The steel is S275 with a capacity of 275 megapascal. Lateral supports at places marked by X only. Find the maximum distributed load according to LRFD load combinations. So what the beam can safely support for the following 3 cases. Assume W includes beam self-weight, and assume the shear and deflections are okay. So we don't have to check for the shear or deflections. So if we take a look at the beginning at this case A, here you have lateral supports in X marks, and it is a simply supported beam, pin and roller, and we're supposed to find WU. Now, in this problem, I have to, first of all, I want to check the compactness. So I can check the compactness of the flanges or the webs, and I can check the compactness of the whole section based on its length. So first thing I'm going to do, I'm going to collect some information I would need in my calculations. These informations I obtained from, there is this part, that is a typo. Okay, so this information I have obtained from the sections table that they are related to IPN 500. Now, these section properties related to IPN 500 I'm using to calculate. First I have LB, LP, and LR, since I'm going to consider the lateral torsional buckling. Now, if you check for that, first of all, let's talk about the length LB. We have to check if LB in here is falling, is it less than LP, or in between LP and LR, or is it bigger than LR? Now, if you check LB, it would be the distance between these 2 X marks, the lateral supports, 2 lateral supports. LB, therefore, is equal to 9 meters. Now, what about LP? In order to compare, LP, there is an equation given to you in the AISC or in your notes where it is 1.76 square root of E divided by Fy multiplied by Ry. Ry is obtained from the section tables. So if you calculate the whole thing, it would appear in millimeters. In here, you can divide by 1,000 to convert it to meters. So in here it appears that LP is equal to 1.76. Now obviously LB is much bigger than LP, so I know that my LB is actually cannot be plastic. Now I have to check whether it's less than LR or not. So I'm going to substitute in my equation of LR. Now here you can see there are many values. Let me show you the equation for LR. Okay, so this is LR. Here is how you're supposed to calculate LR. So 1.95 RTS. What is RTS? RTS, you can calculate it from this equation. The moment of inertia about the weak axis multiplied by CW. CW is something you obtain from the section tables. So we were talking about IPN 500, for example. CW is over here, 1,400 centimeters to the power of 6. If you want to convert it to millimeter to the power of 6, you multiply by 10 to the power of 9. Anyway, let's talk about other terms. SX, the section modulus of elasticity. You can obtain it from the section tables as well. You can calculate RTS. If you do so and substitute 1.95 and EFY, all of them can have. What about J? All right, let's see. J is actually going to be taken from the section tables. Section tables. So J for IPN 500. What is that? J, okay, in here. 402 converted to millimeters. It would become 402 by 10 to the power of 4. What else? Go back to the AIC, my equation. What other terms I have? I have the C. The C I substituted as 1. There are conditions for the C, which are shown in the AIC. And what else? So my case is double symmetric I-shape, that's why it's 1. SX is, again, given in section tables. There is H0. What's that H0? Let's see. So in here, H0 is set as 473. How would I obtain H0? I'm going back to IPN 500. And H0 is going to be the distance between the centroid of the flange to the centroid of the other flange. So the whole thing, the whole depth is 500 minus thickness of flange 27. And what would you get? 500 minus 27, you would get 473 as shown in here. So again, for H0, we show it in here. It is the distance from this point, the centroid of this flange, to that flange. That's your H0. Okay, what else? Now, if you check again your equation, the terms start to repeat. So JC, this is the polar moment of inertia, and all the terms are repeating again. So you substitute everything in the equation and calculate. The LR appears to be 7.88 meters. Now, as you can see in here, LB is actually bigger than LP and bigger than LR. Therefore, we are talking about this region where we will have to use equations that are related to this part. So what are the equations? Now, for that part, we said F2, 2. So these are the equations related, where Mn, let me check, sorry, 2,3 and 2,4, where Mn is equal to FCR by Sx. Sx is given to you in the section table, but you have to calculate FCR. Now, in FCR, in here I have LB, I have it 9 meters, I have RTS, I found. CB is something I'm going to talk about a bit later. I have pi, all the terms, other terms are fine to calculate. So we have to now talk about what? Now we will consider this equation, and now I can talk about the CB. So before talking about the CB, if we check the compactness of this section seems to be compact since the flanges and the web both are compact. The section is compact, but based on what I observed in here, based on the length, the LB was bigger than LR, therefore I have to use this equation related to this line. Okay, now coming to CB, I have to calculate CB to obtain FCR, which can be used to obtain the capacity of this member. So what is CB exactly? You have to draw a moment diagram of the whole beam that you're considering. So in our case, this is the beam and these are the supports, therefore the moment diagram as shown in the blue. Now when I want to calculate CB, it says to you, there is an equation given to you again in AIC in here. So CB, it says equal to 12.5 M max, the maximum moment in your moment diagram, divided by 2.5 M max plus 3 MA, 4 MB, and 3 MC. What are MA, B, C? If you read, it says MA is absolute value of moment at quarter point of the unbraced segment. So if we check in here, the unbraced segment is in between these two lateral supports. Therefore, I will consider a quarter absolute value of moment at quarter point of the unbraced segment. Therefore, I have to check what is the moment at L/4 at this point. Now, if you check from the moment diagram in here, this is your MA. And here we have M max, obviously. What about MB and MC? Continue reading. It says MB is the value of moment at center line of the unbraced segment. Center line. So this is the center line of my unbraced segment. And it appears that MB is actually equal to the maximum moment. Therefore, MB is equal to M max as well. Okay, what else? I have to check for MC. MC is the absolute value of moment at 3/4. Well, since the moment diagram is symmetrical, therefore MC is equal to MA. As shown in here, this is the first quarter and this is the third quarter. If you check the moments, they would be the same. Now, someone might ask me, okay, how am I supposed to find that this is a 3/4 M max? Now, in order to find that, okay, let's say this is MC. In order to find that, let me show you these exact values. Open sketchboard. Okay, so this is something related to statics again. It's like you're finding internal moment at a specific point. So for instance, I want to find the moment, sorry. I want to find the moment at length divided at first quarter of the span over here. Assume that 3/4 is nonsense and you don't know how to get it. So I want to find the internal moment at this point. You will consider a member, a part of your beam. This is the part of the beam with a length of L/4. Now the distributed load would be, okay, let me clear this. The point load that is created by this distributed load, W, if you say that this is W, The point load would be WL divided by 4. And obviously, when you make a cut, section cut, and you're looking for the internal moment, you have such a moment like this, which is the one that you're interested in. Call it MA at length 0.25, the whole span. And obviously, I got the support reaction by considering the whole beam, where this is the whole beam, this is WL. All right, this is WL. Each support would be WL over 2. WL over 2. So this support in here is over there, and I made a section cut in there. I'm considering quarter of the span. So as you can see here, I have this point load from the distributed load, and I have the support, and I have that moment. Now for the equilibrium, take a moment about this point, for instance. MA, take this direction as positive. MA plus WL divided by 4 multiplied by the moment arm, which is L over 8 and minus, since it's going to cause clockwise rotation, WL over 2 multiplied by the moment arm, L over 4. All right, so now all equal to 0. Now, if you open this equation and manipulate it, it appears that MA is going to be equal to, let me check, somewhere there. All right, so MA would appear to be 3 WL squared divided by 32. All right, so as you can see here, I have MA in terms of WL squared. But in my problem, I take it as a ratio of M max. So M max, if you do the same thing for the half of the span, max would be equal to WL squared over 8. Now, if you want the ratio of M max for MA, you would basically take MA, take the whole term, 3WL squared divided by 32, and divide it by the maximum moment, WL squared divided by 8. What would you obtain in here? You would get 0.75 or 3 over 4. Therefore, MA is 75% of M max. And that's how I obtain this value. So you have to check the internal moments if you can find them directly from moment diagrams. Okay, now I have everything set. So I have 2.5 and everything in terms of M max. Why did I do that? So M max cancels out. This M max would go with all the others at the bottom when you sum them up, and you would obtain CB equal to 1.14. Now I want to mention something before I continue. The CB is depending on the shape of the moment diagram. How is that? Let's do it here. The CB, like let's say we had a moment diagram, for instance, where the M max is equal to 1000 kilonewton meter. This is your M max. Now, if you calculate CB for this one, it would be 1.14. All right, what if you had another moment diagram? where M max is equal to, let's say, I don't know, 3000, whatever you like. If you check and calculate again CB, it would appear to be 1.14. Therefore, the CB value is based on the shape of your moment diagram. It's not about the values. But of course, if the moment diagram is different, like this, for instance, the value would be different. Like this shape is different than that one, obviously. So this is something you can consider. Now, before I continue, do you have, guys, a question about the CB? Or do you have a question in general about this problem until here? Okay, seems everything is fine. Now, let me continue. Since we found CB now to be equal to 1.14, I can proceed and calculate FCR from the AISC. Now, again, let me show you from AISC. This is your FCR. That's the equation. You're substituting everything. You have all the values now already. So you substitute everything in this equation, and you get your FCR in terms of megapascal, 189.3. Are you done yet? No, you have to calculate the nominal capacity of this member, where Mn is equal to FCR by Sx. Now notice something, there is a condition, it says to you it should be less than MP. So let's take a look. FCR by Sx. FCR 189 multiplied by the section modulus equal to 520.6. Now, if you compare it with MP, you can calculate MP for this section. I'm not sure if I calculated that in here. Seems like no. I didn't calculate MP in here, but anyway, the MP in this case is actually bigger than this value. Let's say it's actually 700. I'm not sure about this value. So what happens is that you're supposed to calculate the Mn. You obtain it as 520 and check whether it's less than MP or not. So in this case, it is actually less than 700. Now, if it appears that Mn is 800, bigger than MP, then you have to consider Mn equal to MP, 700. Why is that? Because if we go back again to this drawing, you cannot, I mean, this line, the equation that you have is representing this line. And if this line stretches, it's nonsense if your capacity exceeds MP, because MP is the maximum moment or the maximum capacity of the member. Therefore, you limit your result in here and say MP is equal, or Mn is equal to MP. Okay. Do we have any questions about this part of the problem, guys? All right, I'm continuing with the second part, part B now. Oh, sorry, before that, still we have a remaining part. So we calculated the capacity. Now I have to calculate the distributed load. So from the equation that we have here, I found Mn. I multiply it by 0.9 for LRFD. You get your moment 468.54. Now I'm going to assume that Mn is actually equal to Mu, the ultimate moment that can be applied from distributed load. Therefore, 468.54 for Mn factored equal to M ultimate, or the maximum moment we saw from the moment diagram, which is the distributed load by the length of a span divided by 8. So if we check, I think there is a typo in here. I'm not sure if this is supposed to be squared. Okay, it is squared actually. So everything is correct. Now we have in here the distributed load only unknown. So you substitute everything else, you get your distributed load that you can apply equal to 46.27 kilonewton per meter. Therefore, based on the lateral supports that are applied, is on this case, and based on IPN 500, the maximum WU that you can apply, or the ultimate distributed load that you can apply, is equal to 46 point something kilonewton meter. Okay, do we have any questions? Okay, now going to the other part of the problem. Now I'm going to check for the part where it says, let me show you the question again. Now I'm going to consider this part of the problem, part B, case B. In here you can see that I have lateral support at the ends, and I have a lateral support at this point. So I'm going to see the effect of this lateral support. I'm expecting that it would increase the capacity of my member or my section. It can carry load in here more than the load in there. So let's see that. Now, if we consider this case, you don't have to calculate LB, LR, sorry, LB, let's leave it for now. LR, you don't have to calculate again because the section is not changing. LP is going to be the same. Just LB is the one that is going to change. You will check the length of the unbraced section. Now in here, you're supposed to actually check the this length and the other length. So in this case, I have chose 6 meters because it contains the highest moments, and it has a high length. Therefore, I'm expecting that it would suffer from high load or lateral torsional buckling to be correct. So now if I compare LB length 6 meters with those two lengths, as you can see now it is in between. It is somewhere right here. This is my LB. And now I can use the equation from AISC. So if we go back again to AISC, that's the equation that I will be using. So I can obtain MP, can obtain all these values. I already have LB, LP, LR. I just need CB. Now it is true that this section or the moment diagram did not change, but since the bracing or the lateral torsional buckling supports have changed location, therefore I have to consider not all the moment diagram, but I have to consider the moment diagram between these two bracings. Now again, using that equation that we have in AISC, and using the same way I told you about in here, by calculating the moment at a specific point, so 1.5 meters, quarter of 6 meters, and center line, you have MB, and 3/4, you have MC. So if you check the internal moments and everything, you get your M max is actually going to be equal to MA. MB would be equal to 8/9 of M max, and lastly MC would be equal to 5/9 of M max. So we calculate CB from here, and we then substitute in the equation of the AISC F2-2. So this is my CB, and in here I have the plastic moment, MP. This plastic moment is calculated previously, and of course I think I've missed calculating that, but anyway, MP is equal to Fy by Zx. So that's my MP, And again, let's compare it with the AIC. I have another MP term here. That's the term. I have all these things in here. So there is a missing part or a typo where I missed writing 275 multiplied by Sx, the section modulus of elasticity. So 2750 for Sx and 275 for the steel. All right, all the calculations are correct. That's something not to worry about, but I just forgot to write the 275. Now, one more part. We have LB to substitute. LB is 6 meters as we found. Now this is the value of LP, 1.76. This is the LR, and lastly LP. Substitute everything and be careful while calculating this equation. Be careful with the use of parentheses, please, because you might plug in all the values correctly, but because of misusing of parentheses, the value would appear to be wrong. So that's something dangerous. Pay attention to it. Okay, now from here, I calculate my MN. My MN appears to be 746.65. Again, I have to compare it with MP. MP is 890. And it is actually less than MP. Therefore, I can say that the capacity of my member is actually 746 kilonewton meters. Lastly, according to LR of D, I'm multiplying with 0.9, and your member capacity would be 671 kilonewton meters. All right, now this is MN. Assume that Mn is equal to M ultimate, the ultimate moment, where M ultimate is equal to M max, where it is equal to WL square over 8. All right, so we have everything set, and as usual, distributed load is unknown. So from this equation, I calculate the distributed load. Now notice something. In the length in here, we say L squared, you're taking the length of the whole span. You're not going to take LB or LR, taking the length of the whole span, 9 meters. Why? Because the distributed load is actually distributed all over this beam between the supports. Therefore, it is 9 by 9. And you get your maximum distributed load that is allowed to be applied, 66.36 kilonewton per meter. Do you have any questions, guys? Okay, seems not.